Okay, well, so I'm going to talk a bit about the Wolfram language, which is this new thing that I've been working on for 30 years and that has sort of existed in various forms and been gradually being assembled for most of those 30 years. I'll try and keep sort of the organized part of this talk fairly short because I'm actually much more interested in having kind of a more interactive discussion here. First, I think this Wolfram language thing is kind of a big deal. It better be after I've been working on it for 30 years. I think it's something that's just about to sort of emerge in the world, and actually in the next few weeks there'll be the first of a whole sequence of products based on the Wolfram language will be coming out. For those of you who've kind of followed the history of these things, I've pretty much worked on three big projects before in my life, Mathematica, A New Kind of Science, and Wolfram Alpha. The Wolfram language is sort of a thing that's emerged from a combination of Mathematica and Wolfram Alpha, with a few little pieces of New Kind of Science thrown in, together with a bunch of new ideas. Okay, so what's the main point of the Wolfram language? Well, when people think about computer languages, they typically imagine, the language is going to be some very minimal thing, and maybe there are going to be libraries that do particular operations and so on. My concept with the Wolfram language has been to try and sort of use technology as best it can be used, and try and use the technology to automate as much as possible. So typical languages, the language is kept small, the language is great at organizing big code bases and so on. Maybe there are libraries added and so on. The Wolfram language, the idea is make the language as big as possible, make the language do as much as possible, as automatically as possible. Try and have the language be as coherent as possible so that all its different pieces fit together in good ways and so on. But most of all, try and make it so that it is sort of maximally automates what has to be done. Okay, so let's actually try. There we go. Okay, let's see whether 2 + 2 works. Okay, very good. Can you read that in the back? Yes. Yep. No. Maybe. Slightly. Okay, let's make it bigger. Is that better? Yeah? Okay. All right. So you can do you can do all the usual kinds of things that you would expect in any system that I build. There's that goes on for quite a while. That's 10,000 factorial and so on. But one of the important points about the Wolfram language is that not only does it deal with kind of formal types of things, it also deals with things in the real world. So if we, for example, say, let's see where here is. Okay, there's our geoposition right now. Let's say that we want to, for example, make a picture showing showing a disk with a radius of 100 miles, centered on our current geoposition. And let's see what happens if I do this. So this is something that, sort of built right into the language is all of the information that we need to be able to create something like that. Or we could do, I don't know, we could pick, let's say, we could do something like, one of the things when you build a language, there's a question of sort of what are the primitive objects in the language, and kind of one of the ideas of the Wolfram language is that sort of everything in the world should be able to be represented in this language. So, for instance, if I type in, Palo Alto, Palo Alto will be a thing in this language. It's just an entity, and we can say something like, we can look at and the language has built into it lots of knowledge about that entity. So I could say, entity value of Palo Alto, population, and it will tell me probably how many people there were at the last census or whatever in Palo Alto. So kind of the notion is have as much knowledge as possible built into the language. Have knowledge about lots of different kinds of things built into the language. So let's take completely different. Let's take another area. Let's say. I wonder whether I can read in my. See whether I can read in my Facebook graph. That may or may not be possible. Let's see what happens here. This may or may not work because I may have to mess around authenticating and remembering what my Facebook password is and things like that. No, it's a bad sign. All right, I'm gonna use let's use a simulated Facebook graph instead, which actually in my particular case is probably not too far off. let's just have a random graph here, and we can we can just pick up this graph and we can do things with this graph. So we could say make a community graph plot with that graph, and there we'll get the result. Or we could say something like we could try and work out various kinds of parameters of this graph. Let's say we could just say here we could say what does it know how to do with graphs, and they're just all kinds of different things that that you can do in the Wolfram language with graphs. Let's find something interesting. Let's say I just want to find something to do with this graph. Let's find okay, closeness centrality, whatever that is, which I should probably know, but I don't. I probably knew for one brief moment when we were designing that particular piece of functionality. Okay, so we can take this graph, and I can ask for that. Okay, I don't know what this is, but let's see what looks like the kind of thing we might be able to make a histogram out of. Okay, well, we made a histogram out of it. So we can deal with all kinds of different kinds of objects in this language. So for instance, let's see if we can pick up an image. Let's see what we can get here. Oh, what's that? That's me in front of the screen. Let's try. Well, okay. And we could we can take this image and we could say we can do operations on this image. We can say something like let's say image partition of that image into little blocks of size 20 or something, and there's another version of that image. Or we could say, for example, something like let's do. How about we sort? Let's say flatten that out into just a bunch of little images there, and let's sort that by. Let's say we can sort it by. Let's just look at the average of the average pixel value basically in each image here. So let's try doing this. So that will do that. Let's see what happens there. Okay, now we sorted it by average pixel value. Now let's partition that back into something of size. I don't know how big that is. Let's take a look. How long is that? Let's pick that up and just say length of this. So let's see, we make a partition of that. Now we can say image assemble, and now I bet it will be absolutely, yes, it's completely scrambled. And we can go ahead, if we want to, we can have this stuff work dynamically. So for example, we could say something like dynamic of, let's just say edge detect or something, of the current image, and we could get this up, and now it'll, I can wave my hands and so on, and it should be able to deal with that. We could also take, we could also start, so kind of the concept in all of this is be able to deal with also to different kinds of objects, be able to sort of automate as much as possible how one deals with those objects, not have to know the specific algorithms that might be used for some particular kind of thing, but just sort of automatically pick the best way to do a particular computation. So, well, there's all kinds of so a typical thing that happens these days is that when we are setting up algorithms for things, the problem is more to build meta algorithms than to build individual algorithms. So there may be some particular thing like, I don't know, solving some partial differential equation or something for which there might be 100 different particular algorithms. And in fact, some of the most difficult work ends up being sort of building the meta algorithm which decides for any particular partial differential equation which specific one of those 100 different algorithms should one actually use. And that's sort of an interesting kind of, that's the evolution of what's happened in sort of algorithm design. A lot of it is involved with those kinds of things. Another thing I might say actually about algorithms that's sort of interesting is, in the Wolfram language, we've made a great deal of effort to sort of be able to deal with lots of very different kinds of objects in the language. We can do sort of sophisticated computational geometry, and we can do, combinatorial optimization, and we can do all these different kinds of things. Well, it used to be the case that when you were specifically trying to build, let's say, a numerical algorithm, that the thing you needed to do, that the best way to do that was to just build this tower that was all about building numerical algorithms. This is very definitely no longer the case. The best modern algorithms are ones which end up being, maybe it's in the end going to be a numerical algorithm, but somewhere in the middle of working out what has to be done for that algorithm, you're dealing with some kind of geometry problem, or you're doing some algebraic transformation, or something like that. So the building blocks for sort of the modern algorithms end up being these big building blocks that come from all these different areas of kind of algorithmic work. And that's something that's been pretty important for us, because as time has gone on and we've added thousands and thousands of different kinds of algorithms to our system, it's been important we're sort of able to do that at an accelerating speed, because we have these big building blocks that come from all these different areas of kind of algorithmic work. Well, so another big thing, as I say, about the Wolfram language is being able to deal not just with the abstract, but also with sort of concrete things about the world. So, and if I ask it something like sunrise, it will tell me, that's, I guess, the time of the next sunrise. Or if I say something like, let's try this, see if this works. Air temperature data here. See what it does. Maybe it'll work, maybe it won't. It's a little surprising. I would expect it will, let's see what, it should be telling us the air temperature here. And I don't know why it isn't. Well, I'm showing you something that doesn't actually exist as a product out in the world, so there's an excuse. It's got another 2 weeks to be able to do everything correctly. That's a bit surprising.
Stanford may be throttling for some reason.
That's possible. My computer just sitting here is not going to know the answer to this. It has to go out to the outside world to be able to work that out. Well, let's try. That's bad. Let's see. Kill that and see what happens if I just do this. I'll try one more time, and if this doesn't work, we give up and go on to something else. I think so. Well, for some reason this is not working. Let's see whether anything is working and that requires going to the outside world. This is very odd. Very odd. Okay. Let's try something else. Let's try flags of countries in South America. So one thing I'm doing here is mixing natural language with, see what I get here. Okay, I get something. Actually, let me just do something different here. Let me just say countries in South America. The thing that's interesting here is that we're mixing kind of natural language with sort of the precise language. This is very weird. Why is this not working?
Are you connected to the network?
I certainly hope so.
Try opening your browser window and seeing. You might have to accept the.
Let's go there. Let's see whether that works. That's rather slow, but working. That's really odd. Well, this is going to be no fun if this doesn't. It doesn't. This is the terrible thing. It used to be the case one could give a demo that was just on the computer locally, and that's now. All right, come on. This has got to. No, this is really odd. Especially it's odd because it started off working just fine. And I'm really confused by the fact that it even refuses to quit. Oh dear. What's that? Let's hope not. Let me see. I'm just going to try. Let's try something else. See whether anything is alive here. This is not a very good sign. All right, I'm going to I can't imagine why I need to do this, but I'm going to restart it. See whether this makes any difference to anything. Okay, size 125. And I'm going to try the exact same thing again and see whether it fails in exactly the same horrible way again. Okay, I am really confused. This is something that's worked for 5 years.
So you need to add diagnostic stuff to the system, huh?
I guess so. We have lovely automated tests, but this is also the that's really odd. Let's see whether anything is working here. So let's try just asking it about a place. Okay, that worked. Okay, I'm totally confused. Well, who knows? All right, let's so the thing I was trying to talk about. How about let's pick up another. Let's see whether things work. Okay, that worked. A little bit, not much.
Whether you didn't do good.
Yeah, no, I mean it has a whole elaborate caching structure, but I'm just really surprised that it doesn't know how to do that. Anyway, so kind of the as I was saying, kind of the idea is to be able to have in the language lots of knowledge about the world as the world is. This is something, and as we built Wolfram Alpha, we've been accumulating lots of kind of knowledge about the world, lots of different domains of data, lots of different models and methods and so on to compute from that data. And all of this is we're now able to flow into this language so that you can kind of manipulate it in a systematic way. I mean, presumably, let's do another geographic kind of thing, and it's probably going to fail again, but let's just try. Let's say, find the 10 nearest cities to here or something. This is a typical kind of computation. Come on. This is really odd.
You may be being firewalled off.
No, it's using HTTP. It's
Plus the owl.
yeah. How can the owl be here? It's just weird.
Clever firewall.
Network operation timed out. Okay, well, at least it knows that that's what happened. Okay, that's really odd.
Maybe it's down.
No, it's ours. So if it's down, our whole infrastructure is down. And I kind of know it isn't because I just went to Wolfram Alpha and it worked just fine. So it's the same. Plus much wouldn't work if that was down. Even more wouldn't work if that was down. So, well, in any case, I was well. Let me show you. So as I say, the idea is sort of have as many algorithms as possible built into the language, have as much sort of automation as possible built into the language, have as much knowledge as possible built into the language, sort of build as many kinds of things into the language as possible. So one of the questions is, well, what should the foundations of a language that's going to have lots and lots of stuff built into it actually be? And this was something I kind of thought about a really long time ago. And the first computer language I built, which was in 1980, I kind of got deeply involved with the idea of symbolic computation and the idea of representing sort of anything that you could deal with as a symbolic expression. So what does that mean? If you have some expression, x squared plus y squared or something, this is a thing which in full form is just some plus of power and so on. But anything is represented in the same kind of way. So I mean, if I have a picture of a 3D graphic or something like this, that's also just the same kind of thing. It's just some graphics 3D of sphere, of list, of so on. So any kind of object is represented in this very uniform way as a symbolic expression. And this is a pretty important thing because, when we have something like our sort of thing like, I don't know what, an aardvark or something, Okay, there's an aardvark, and the aardvark is also represented in the same kind of uniform symbolic way. So once you're dealing with things in a sort of uniform symbolic way, you get to have operations that can sort of act on arbitrary symbolic expressions. So here's a typical sort of iteration construct. We could have something where we say, put a frame around it. We could do something like this. We could use the exact same operation. We could say, let's say, let's say edge detect an image. Let's pick up one of those images we had before. We can pick up this guy here. And just put, because it's all symbolic, we can just, the image is as good as anything else to put in there, and we can, successively edge detect the owl if we want to. And we can do the same. We can treat sort of everything as a symbolic expression. One of the things that's happened over the 25 years since we released Mathematica and so on is that every few years I've realized that another kind of thing can be represented as symbolic expressions. So in the very early days it was things like mathematical expressions. Then it was things like graphics. Then it was things like documents. Then it was things like user interfaces and so on. So for instance, if we want to represent user interfaces symbolically, there's a slider. I could perfectly well just make a table of sliders. So I could say, for example, let's put a random number into each slider. Let's put it so that will make the slider be in a random position. And let's say we went to a 5x5 array of sliders. So that wasn't so elegant. Let's make it a little bit more elegant. There we go. So here are a bunch of sliders, and we could connect them up to things, and we can just treat this interface as a symbolic thing. We could even, if we wanted to, we could make some funky interface by nesting. For example, let's do this. This is going to do something really weird, I suspect. I have no idea what this will actually do, but let's try it. Well, that wasn't too weird. How about here? Does it make any difference? Let's see. If I just add another thing there, make that go, 10 levels or something. What is it doing? What is it doing? Maybe making something absolutely huge. I haven't thought about what it's actually going to do here. Oh, it did something. Okay, there we go. So, we should have an operable nested user interface for what it's worth here. But the important point is that all these things are just symbolic expressions that we can manipulate, and we could pick up and do things with. If we pick up these things here, we could deal with these. We could say, rotate. Well, how about we do this? We just say manipulate those symbolic expressions, rotate those symbolic expressions. Actually, let me do this. Let me say rotate them by a certain angle, theta, and I want to make the angle variable. So I go here, I say theta from 0 to 2 pi, let's say, and now I should have something which is a little interface there where I can go and rotate this thing around and so on. So, lots of different things that sort of come together in this symbolic language. Okay, here's a big sort of new thing that I realized only fairly recently, which is that another sort of element that can be thought about symbolically is things in the cloud. So, for example, I could go ahead and I could say something like cloud deploy, something like hello world, and now I could go, and what will happen is, oh great. And the embarrassment will be that my own cloud doesn't let me in, but we shall see. Come on, there we go. Okay, so what this did was it deployed the simple thing hello world to the cloud. It wasn't very exciting. It just made a web page that said hello world. We can make it a little bit more exciting. We could say deploy to the cloud something which has a style, size 100, and let's say let's deploy that as a PNG, and then we can go ahead and do that, and now we'll get this thing deployed to the cloud like that. Okay, let's make it a little bit more interesting. Let's say we want to deploy a form to the cloud. So all we have to do here, we just symbolically create something that says we have a form function here, and we'll have a thing that says, let's say we say angle, and that angle is going to be a number. And we can now go and say, instead of this, we'll just say something like rotate that thing by an angle by hash angle there. And now I want to say that's a function there. Okay, let's see, what did I do wrong here? And I want to say, yes, like that, I think. Okay, so now what this is supposed to be doing is saying create a form, deploy to the cloud something which is a form, wake up, there we go, which says type in an angle. Oh, it's probably, this is an angle in radians, but let's say, okay, let's say, I don't know, 1.2 or something. It's in, I should have made it in degrees, but I didn't. Oh, what did I do wrong here? And that is lovely, but not what we wanted. Okay, let's see, what did we do wrong? I should have said, that might not help. Rotate that by that angle. There we go. Okay, let's try this. So now we should get this form up. And now let's try typing in our 1.2, try submitting it, and hopefully, there we go. Okay, so there we get our hello world, which we've now able to just, with this little piece of symbolic code, we're able to get this form deployed in the cloud, and we could do any computation we want here. So, for example, and we're also able to, we could, for example, let's say we wanted to deploy in the cloud something which is actually an active thing that we could, where we can manipulate something. Let's try doing that. We can say deploy this. Okay, manipulate that with an angle from 0 to 2 pi or something. Let's see what happens if we do this. This should, I hope. What does this do? This actually brings up a bit more framing than I would hope it would have to, but it should work. There we go. So now we have something which, where we've deployed that little user interface to the cloud, and every time we move that slider, it will go back and do the computation to work out what the image should be. Well, we can also do some fun things by using the fact that we have natural language understanding built into the system. So if there's a function called interpreter, which will just interpret things. So for example, if I say interpreter of, New York City here or something, it will go ahead and take that and turn it into a canonical entity like this. So if I say something like interpreter, the Big Apple or something, we get the same kind of object. Well, now we could go ahead and say, cloud deploy of a form where the thing that we have here is the name of a city. We say it's going to be of type city, and now let's say we make, that thing I was doing at the beginning where I make geographics of that city entity, and then let's make a disk around that. Let's say, no, I'll tell you what. Let's do this. Let's make a let's do this geo list plot of that city, comma here, and now let's make that joined. Let's join that line, and then let's say, okay, that's a form function. We want to make that produce a PNG rather than just produce some internal code. Now, oops, wrong thing to do here. I should have done that. Let's see, what do I want to do here? I want to do that. There, okay. All right, so now I should be able to deploy that to the cloud. Let's try something like London. Let's try just submitting that. And now what should happen, if we're lucky, is that it will go to our cloud and, oh, come on, okay, there we go. And make a picture there that we just told it. We just said make a geo list plot of the city, and here maybe we can just say geo range arrow world, for example, and then we'll make the same thing. And let's make it a little bit bigger. Let's say let's go ahead and say magnify that by a factor of 2 or something. So now let's do the same thing. Let's say Berlin or something. Let's see whether it works here. Okay, there we go. So I think it's pretty neat that you can write just one line of code here and have stuff like that work. I think it's neat. And it's sort of surprising how much stuff is in the system. I mean, I was somebody was asking me a few days ago for very bizarre reasons at some hackathon. They said they were making some app about cat breeds, and so I said, I'm pretty sure we have data about cat breeds here. Let's see what happens. And so this should be something where if I type in I can do something where I type in a cat breed and I can get. Let's see whether this works. Oh, actually, we can just do this locally if we want to. We don't have to go out to the cloud. We can just make all this stuff happen locally here. Maybe not. What did I do wrong? Let's have this go to the cloud. So we can try having a thing where the interpretation, what we're typing in here, this is sort of a smart field that allows us to enter natural language here. So let's say Siamese cat or something here, and see whether it works. Okay, sort of surprising that you can do that just out of the box with a computer language, but you can. So we've tried to put into the Wolfram language lots and lots of knowledge, lots and lots of kinds of computations, whether it's all sorts of sophisticated visualization, whether it's things to do with data. Oh, here's something I can show you. Let's say you want to do machine learning or something. So you could say there might be a built-in classifier here that will do sentiment analysis. Okay, that's a good sign. We can also just give it some actual training set and tell it. Let's see if we can get an example of that. For example, let's see here. Let's just look up. If we the idea would be here. Let's do an example here. Let's take that training set, and it's a pretty simple training set. And now we can just take that, and it will figure out. For this particular case, it's going to use multi-logistic method, and there are 10 classes of things here. And now we have a classifier function. This thing is just a symbolic object. It's just a symbolic function. We can just take that function. Let's call it fun or something, and we can just say fun of. And then we could even let's see if I can really be ambitious here. Let's try. I'm going to do something ambitious, which will almost certainly not work. I'm going to try and actually draw a something in here. Let's see what we can do here. Let's do this. Let's make a new thing there. Let's make something like this, and let's try. I bet this gives the wrong answer, but let's see what happens. Let's try. Well, it's not going to be helped by the fact that it's a lousy 8. Let's see. Okay, that's life in the world of machine learning, especially with a training set of that size. But anyway, the idea is, and it will obviously work with much, much larger training sets and do much better, and it uses all kinds of fine state-of-the-art methods and so on. This is a pretty typical example of a place where one's interested in algorithm automation and where one's dealing with, given the particular data that's been provided, what's the best algorithm to use. Let's see here. I mean, lots of other kinds of things. Things to do with geometry, that's kind of interesting. Let me show you something with geometry. We can take something like, let's say we take a set of random points. So let's take random real, let's take coordinates in the range 0 to 100. Let's take 100 random points, each with 3 coordinates. Okay, so there's that list. And now let's make a Delaunay mesh around those points. So we go ahead and there's our mesh in 3D. And what's interesting is we can pick this thing up and we can do things like say, what's the volume of this object? And it can just figure that out. And that's, or what, if we want to do, let's try this, just to tempt fate. Let's do region. Okay, I'm going to do something just because let's see, of region nearest of that. And let's do something that is a point, let's say 0, 0, 0, Z. And let's make, I always have to do stuff like this. I have no idea if this is going to work, but I just had the idea of trying this. So let's go to 200 or something. So what this should be doing, oh no, that's actually what I want is region distance. So what that should do, I think, is to, yeah, there we go. So what that's doing is it's taking a point, the point 00z, and it's working out the distance of that point to the nearest point on this mesh that we just created. I think that's, again, I think the kind of automation that's necessary to make stuff like that work is quite large. Okay, so other kinds of things in the language. Well, lots of kinds of data. I showed you a little bit of geographic data. We've got data on lots and lots of kinds of things. Well, I don't know, we could do a genome lookup or something against the human genome. That's all sort of built-in stuff. We could make something, we could do something, we could say in our language, we could have something like, how about this, we say avatar. And hopefully it will know that that's a movie. Okay, so let's say, what do you know about that movie? What are the properties of that entity that you know? Okay, so here are a bunch of properties of that entity that it knows. And so, for example, we might say, entity value of that avatar thing, and say, show us an image or something related to that. And then there we have the movie image or whatever. Of course, we have all sorts of fancy math kinds of things, from the heritage in Mathematica. We have lots of ability to deal with the external world. So there's lots of elaborate kind of templating mechanisms and so on, where you can define an XML template, for example, and then inject kind of symbolic code inside the XML template, and then assemble your website. You can also let me show you another thing. You can also take one of these things that we made here. Let's say which one? Let's take our cat breed example. And instead of making this a form that we deploy on the web, we could make this an API that we deploy on the web. So, for example, here we could do this, and now we'll get something which is just a RESTful API. And if we don't give it any parameters, it'll say parameter for cat breeds is required. So if we say cat equals Burmese or something up here, we will have just created an API that retrieves pictures of cats in this particular case. So we can also, so let's say we want to call that API from something, so that's calling the API from just a web URL. We can also say create the embed code for that API for a language like, let's say, Java or something. And now what will happen is we'll get a piece of Java code, which is a wrapper for calling that API from within your program. And so the idea is that you can create sort of a piece of Wolfram language code, and then create and set it up so that you can call it from inside any kind of other programming language or any other kind of system. Well, I should say when we're writing kind of Wolfram language code, you can see you can do a lot with just a small amount of code. You can build big programs in this language as well. The biggest program I know of that's been built in this language is Wolfram Alpha, which is about 15 million lines of Wolfram language code. And it's sort of interesting what that code looks like, because it's sort of a mixture of, because everything is symbolic, the data, the code, everything is represented in a uniform kind of way. When you look at like the natural language understanding system of Wolfram Alpha, it's sort of a mixture of stuff that looks a bit like data, and these little algorithmic pieces inside the data, because the data and the algorithmic pieces are all represented in the same kind of way. But when you start doing this, it's pretty useful to be able to add annotation to all this. It's pretty useful to be able to have sort of an interactive environment where you can create your program. We have had for a long time this notion of notebooks, which are these kind of interactive documents, these notebooks, there's a thing we call CDF, a computable document format, which is kind of the format of these notebooks, and it can be deployed in lots of places. And in particular, now it's possible to deploy it purely on the web. It's been able to be deployed in a browser plugin on the web, but you can now deploy it purely on the web with Cloud CDF, where everything is happening purely in the web browser, and then for the computations it needs, it's going to our cloud backend. And I should say that sort of everything I've been doing actually is doable in the cloud. So in fact, if you go, and this will be in about 2 weeks, I hope, this will actually be something live and available to everybody. But we can go ahead and try and do this. Everything that we've been doing, we can do purely in a web browser in the cloud. So this is just, there's nothing, I can go ahead and I can say, you know, if I make some plot or something, I can go ahead and do that right here, just using this web browser. And now every time I move the slider, it's going to have to go to our server to go and get the computation done. But I could go ahead here and I could be writing code and I can say cloud deploy from here and so on. So everything I'm doing is just available directly from the cloud. And you can take this little piece here and you can embed this anywhere you want. So you have sort of a immediate programmability that you can add to things. And there are lots of different ways that you can deploy. I mentioned some of them. There's this instant API notion, instant web computation. There's things like being able to have various kinds of embeddable content and so on, being able to create mobile apps. If I went back, well, I can do it from either. I can either do it from the web or I can do it from the local client. But if I went ahead and just said, took one of these cloud deployed things, I could, well, yeah, if all I have to do is deploy this publicly, and it will start showing up inside our mobile, inside our cloud app, and you can then use that. Use the interface from within a mobile device, and it gets some extra pieces. Like, for example, if you create a form that is expecting an image somewhere, then that image can be picked up just from the camera in the mobile device, and all those kinds of things. So this is so that's kind of the idea is to sort of have universal deployment of this language, whether the language is being deployed, whether it's operating on a single machine, whether it's in the cloud, whether it's being used on the web, and all those kinds of things. Actually, it's worth saying that we also have this notion of an embedded Wolfram engine. So taking the engine that runs this language and being able to embed it in lots of different places. So I showed here, this is a piece of Java code which is set up to just call our cloud to get a computation done. But if you have an embedded Wolfram engine locally on some machine, this Java code can be set up instead to call that local embedded engine rather than calling us over through the cloud. And in fact, this notion of embedding the Wolfram engine in things, there's lots of different kinds of things you can imagine embedding it in. It's kind of a fun thing to try and figure it out. We've been trying to figure this out. So you can embed it in IDEs, for example. So you can be going along inside, some random Eclipse IDE or something like that, and you can say, I think I'm writing Python code, but actually now I have something I need to do with Wolfram language stuff. And you just pop up a little window, write your Wolfram language code, press go, and it will sort of create the relevant call either to our cloud or to a local embedded engine, and sort of connect those things together and have the code that you need created within the IDE. Or another example, let me try and show you another example. Let's see if I can do this. Another fun example is embedding the Wolfram language inside, let me see whether I have something here. Inside Unity 3D, let's see whether I have this. No, that's probably not a good place. Okay, I have an idea. Let me see if I can show you this. Oh, come on. If I'm lucky, there will be something there. No, let's try this. No. Oh well, let me see. I have one last place I might be able to find this. I'm sorry if I can't do it. No, this is not going to work. What I was hoping to do is to show you being able to, it's kind of neat, being able to control Unity 3D from inside the Wolfram language and being able to take data from Unity 3D and send it to the Wolfram language. That's sort of interesting because it's kind of an embedding of our language inside, in this particular case, a game engine. And there are all kinds of other embeddings you can imagine. You can imagine embedding inside a spreadsheet. You can imagine embedding inside all kinds of things. Another place that we've been quite involved is with devices and the sort of Internet of Things and so on. Actually, I was curious recently. A very simple question, which was, what are all the things out there? And so we have this project to sort of curate what kinds of things people are making that are connected devices, and I think there are about 2,700 of them that we've found so far, and they do all kinds of different things. You can look at all the different quantities they measure. There are an embarrassing number that measure, that are pedometers, but there are also plenty that measure all kinds of much wilder sorts of things. So one of our goals is to be able to let our language connect to all these kinds of devices, to have a way to get data from all these devices into our language. And we have one very interesting feature of our language, which is that in our language, because we have representations of real things in the world, the kind of, a device that says, I'm measuring voltage, or I'm measuring, resistivity, or I'm measuring, the number of sheep walking at this, past this thing. We actually have representations of these kinds of objects in our language. And so we have this thing we call WDF, Wolfram Data Framework, which is kind of a way of representing things in the world in a precise symbolic form. And so the idea is to take data that comes from all these different kinds of devices and put it into WDF. And once you have it in WDF, you can compute with it, and you can do all sorts of fancy time series analysis or correlations or predictions or whatever you want. But all these different devices, wherever they come from, can consistently put their data in this WDF form. So, for example, the main thing that we're dealing with, the first thing we're dealing with is once a device kind of makes web contact, once a device can actually send its data to the web, then we have a kind of a device analytics platform that we're building that will take that data and be able to do interesting things with it and be able to let you create a dashboard or create an instant API or whatever to work with that. And so so one kind of thing is being able to take data from devices in a consistent way and do things with it. Another thing that we've been interested in is actually getting the Wolfram language to run on devices. And so, for example, one thing we did, that's the Wolfram language homepage. One thing we did late last year was to start bundling the Wolfram language with every Raspberry Pi computer that goes out. And that's just a preliminary version of the language. There'll be more recent versions of the language coming to the Raspberry Pi soon. It's sort of interesting to see what you can do when you have a persistent running Wolfram language engine on these devices, these $25 computers scattered around the place. Again, it's kind of a whole story of symbolic objects, because the running Wolfram engine on every Raspberry Pi is itself a symbolic object. And you can do things like do a parallel computation across all of those Wolfram engines just by using a simple command that's just built into the language and operating on symbolic objects, which happen to be, in this case, running Wolfram engines. So that's kind of an interesting feature of those sorts of things. And I think one of the things that we'll see in the next not too many months, I'm hoping that we'll have a moment when, I think it'll happen more or less the same time, when we have the Wolfram engine running on the very, very tiniest possible computers and the very, very largest possible supercomputers. And both things are being worked on, and they'll probably happen about the same time. And so it's really interesting to be able to have this language that spans, things that can be built into devices, can do local processing inside a device, can send data to the cloud, can do fancy processing in the cloud, can operate in mobile. I should say that the kernel of the Wolfram engine runs on iOS and Android, not yet released though. The whole interface mechanism, we have kind of a native interface under iOS that will hopefully soon be released, but it's been rather painful to finish that. So let's see. Well, there's all kinds of things that I might talk about here. Another thing I might show is, let's see if I can do this. Let's see if this works. I have a bad feeling none of this is going to work. I was going to show you is something that we have, which will soon be fully integrated into language, is the ability to deal with systems engineering objects. So, for example, we have a product called System Modeler, which has kind of had a separate lineage from our other products, but it's a way of representing kind of large-scale systems, engineering systems. So you can routinely, represent a gas turbine with 50,000 components and so on, and derive the equations that represent how that system will work. And you can set it up so that within, not quite yet all integrated, but soon will be, within the Wolfram language, you'll be able to just simulate that whole system and do computations about it and so on. And so kind of the view that one eventually has is that one can do things like the following. You can go from sort of a voice input to natural language. You can interpret the natural language, which we've gotten pretty good at doing. You can get some sort of precise symbolic representation. That symbolic representation represents something about some giant machine that you have in front of you. You can then simulate what the giant machine is doing, and at the end of it, you can just ask your phone or whatever, what's going to happen if I move this red lever from here to here, and the thing will compute what's going to happen, and it'll tell you that's a bad idea or whatever else. But it's sort of interesting to see this whole stack of technology from kind of the simple sort of consumer voice input down to the simulation of some giant device, all happening inside this language. Well, so one of the problems is, okay, so we have this language and it you can do lots of things with it. What are you actually going to make with it? This is probably not that's a good list. That's not a bad list. Let's see. There we go. That might have something good. We have a number of things which we're making with this language. So the first thing that will come out is a thing called the programming cloud, and the purpose of that is it's something where you can do development either in the cloud or on the desktop, and the purpose is to create deployable things. So I showed you a few examples of that where you can deploy, a form-based app, or you can deploy an API and so on. The purpose of the programming cloud is to provide a way to go from sort of an algorithmic idea to a deployed thing as quickly as possible. And it's kind of I have this feeling that there's an awful lot of pent-up kind of algorithmic startup ideas out there, where it's just a question of, there's an algorithmic idea, but the distance from the algorithmic idea to an actual deployed thing is too far for it to ever have been done. And I'm kind of expecting that when the programming cloud comes out, that we'll see kind of a wave of sort of algorithmic startups that are now possible. Another thing that is coming soon. Oh, it's not listed there. Okay, it's coming too far away. Okay. Another thing we have is I mentioned our device analytics platform for dealing with data from devices. Another thing is a data science platform aimed at data scientists. One of the things that makes use of is a mechanism using our CDF mechanism. And as I said, documents, like everything else in our world, documents are symbolic. So, for example, we can just create a document here, and we can say time. Let's say we can say an expression here. We can say a date string. Oops. Date there. We can say something like I don't know. Whatever. We could do anything we want here. We can. This is a symbolic object that is a template for a document. And if we say generate that, not terribly exciting in this case, it will generate a document that has filled in what the value of that date string is. Where this gets much more interesting is when this is pulling data from some database and doing all sorts of computations, generating a report, being able to feed that report through an API out to wherever you want to send it, and so on. So that's one big thing that you'll see in the data science platform. Well, another thing that I've become interested in is, so how do we use this stuff? Programming, this sort of changes the economics of programming, changes the character of what it means to do programming. Where can we use that? Well, one very interesting place to use that is in programming education. Learning to program is a really useful thing in the world today. How do you learn to program? You can start off learning Scratch or something, but you're not going to be using Scratch for very long. Or you have to dive into a fairly complicated language where it takes quite a long time to get to anything that has anything real happening. The thing that's really great about this language, as you could see, is you type a line of code and something real and connected to the world actually happens. So, in fact, I've been pretty encouraged in the last few weeks, actually, since we started talking about this language. A bunch I've been quite deluged with people pointing out to me the fact that this is a good language for programming education, which is always a good sign. So we've been trying to figure out, so how should you teach programming, given that this is the language that one's going to use? And there are a lot of very interesting features of this language. One thing is, when you have a symbolic language, every fragment of code means something. So there's no notion of you have to build a big program and then see what it does. Any tiny fragment is already meaningful. It may not do anything very interesting, but it's already meaningful. So you can build things up in pieces. It's also a language that is realistic to learn by sort of immersion. I mean, if you have a language which is pretty complicated, you've got some great big, C program or something. If you just show people, here's a C program, it does this. It's rather difficult for people to go from that to something which is to sort of their variant of this. Whereas with our language, I think it is pretty realistic for people to just go from examples and to deduce what to do and tweak those examples and so on. And we've seen that with Mathematica. We have maybe 200,000 examples now in the documentation for Mathematica, and the typical kind of mode of operation of people is they go look at the examples, they tweak them, and get to what they want to have happen. But something that I've been interested in is how do we best set up? I mean, if we look at mathematics, for example, it's had 1,000 years to decide what sort of the order of concepts to teach is. It's not so clear what you do in programming when you have sort of access to sort of knowledge about the world and so on. Now, you can start off. Because we have these natural language capabilities, you can start off. Let's see what this. I said something kind of stupid there, but let's see whether it can. Let's see whether it does anything. Blah! Well, so it goes. Let's say something like that will probably work. You can start off kind of just using pure natural language. To create fragments of code that you can then assemble and do things with. And that's sort of one mode of programming, is to just start with natural language. Another mode is to sort of start with some piece of code that already works and so on. And so one of the interesting things, I think, will be to see sort of how can you teach people programming in that kind of way. And the thing that's neat, of course, is that this is not a toy language. This is a language which, at least in its version in Mathematica, has been used by lots of the world's finest R&D folk for years and years and years, and we know we can build big programs with it and so on. So it's a language that kind of goes from the first thing you try to learn to program with to the thing that you can use to build real stuff. Well, so I'd be happy to talk about lots of different topics related to this. I can talk about kind of the how one thinks about designing a big system like this. If people are interested in that, I can talk about more practicalities of what the system can actually do. But maybe I should stop here and turn this over for. I thought there'd be more questions in the course of this, but please, yes.
So I have to ask the question, for instance, in terms of the static versus dynamic binding. But you were showing in the case of units, does a given copy understand whether or not somebody is within the Imperial English system versus the metric MKS or CGS system?
Yeah, so it'll default to, I'm sure if it says, there's a dollar geolocation country, it'll default to, okay, so it's in the US.
But is this static or is this dynamic?
What do you mean by dynamic?
Dynamic, in other words, for instance, you cross a national border, it understands.
Yeah, I think when you ask it to, if I asked it, default distance, I don't know, if I say geodistance between here and I don't know what, New York City or something. I think that will probably get quoted in miles here. It got quoted in kilometers here. That's a surprise. That's a surprise. It doesn't seem right to me.
That's the kind of question that's
That's good for Stanford. We wouldn't.
I'm surprised. I think you can reset dollar geolocation country or something else.
Is that static or is that dynamic? As if you move around?
Oh, when you compute it, so when you run the computation, I think it will look up what country you're in and figure out what to do, I think. If you want to, you can use this dynamic construct. If I say, dynamic of date string, for example, you should see it, I hope. Maybe I have to tell it to explicitly to refresh. I think maybe this doesn't, this you may have to tell it to refresh. Let's see. In a case like this, hopefully it will count up and so on. So some things you can, but usually what happens is at the time when the computation is done, that's when you'll get what you get. And so, for example, if you're calling an API, it certainly knows when the API is called. It absolutely knows what what all sorts of things about the user who is calling the API. It knows about who created the API, but it also knows about who's calling the API, and it will dynamically decide. If it's being called from a mobile device, it will know what the geolocation is and all those kinds of things. And I'm really surprised that gave a result in kilometers. That doesn't seem right.
Well, not that too. I mean, in Europe, the use of the decimal point varies between decimal points and commas as well too.
We're very well aware of it. In the case of Wolfram Alpha, that it goes through many backflips to deal with queries that come in from countries where the use of commas and periods for numbers is interchanged. It's a very painful thing. Yes.
I think there's another Palo Alto in Texas. Do you have a way to deal with ambiguity? There's another Palo Alto in Texas, I think. Do you have a way to deal with ambiguity?
Yes, absolutely. So in fact, if you see, I'm sure if you type Palo Alto here, you see those ... dots? Those say, okay, there's one in Mexico, there's one in Pennsylvania, apparently. This is for God's sake, whatever. It should have done the right thing. Let's see, is that the one? Okay, it switched to being the one in Pennsylvania. That's something we've developed a lot for Wolfram Alpha over the last 5 years, and we've been able to see the extent to which people go to the non-standard choice. We have a bunch of heuristics, like for cities, based on geolocation and size of city, and how famous is the city, and things like this. The thing that surprised me, actually, is how right we managed to get it. In other words, the number of clickovers of people where we got it wrong is surprisingly small. And we've tried to do that across a lot of different domains. That's how it works. And you can access this programmatically. There's a whole ambiguity function mechanism for the interpreter, and it gets quite complicated. And particularly when you have multiple things which sort of where the ambiguity of one of them, where when you change one of them, it affects the likely context of the other one. There's all kinds of stuff that we've done in Wolfram Alpha, and that is mostly accessible in the language for dealing with that. Yeah, please.
In the browser, do you have an engine that runs in JavaScript or native client or something like that, so you can get the computation happening directly on the browser window?
Well, okay, so our full Wolfram engine, this is a big thing, okay, and it has all these data feeds, and it's got terabytes of data and so on. It's not going to run in the browser anytime soon. What we're running in the browser right now is purely the user interface. Now, what we will be able to do increasingly, an increasing number of things, we're able to take sort of a compiled version of the symbolic code and push it into JavaScript and push it up to the browser. Okay, but we won't be able to do that for everything. And we're doing some crazy things with mscriptm and transcompilation of things. The likelihood of us being able to transcompile our whole engine into JavaScript is low. The fact that that's even something one imagines doing is kind of crazy. But so in other words, what's happening is the vast majority of serious computations will go on in our cloud. But what we're going to push up to the browser. Yes.
On the subject of learning the language, I'm curious how far you can imagine the discoverability going? I mean, taking one of your early examples, could someone encounter the system for the first time and say, I'd like to take a photo with this webcam and divide it into 20 by 20 pixel boxes and sort those by average hue and then reassemble them in the original form in natural language? And could you imagine the system coaching the person through how to do that, or doing it directly, or is that still science fiction?
Well, we've been working on things like that. I mean, there's several issues here. So when you describe a program, right, actually, natural language is a pretty poor way to describe most kinds of things that you put in programs. And in fact, it's so bad that in our attempt to find a corpus of places where people have described things that they do in programs in natural language, there really aren't, that we can find very good corpuses of that. So it's just not something one ends up wanting to do. I mean, it ends up being something where what I've been surprised by and interested in is this notion of, typing control equals and getting these little boxes and being able to enter little fragments of natural language. This is really useful. And for example, whenever you have something related to the real world, being able to enter a fragment of natural language that refers to a type of, some species of lizard or something in the real world, it's really useful to be able to do that in natural language and not to have to go to the manual, which has, some giant list of different types of lizards or something. The question of being able to do the programmatic, the stuff that relates to, actual structure of programs and things, we're working on it. It's, I think some things will come more easily than others. I think the notion of taking something and making hints. So one thing that's interesting in our language, because code and data are the same thing, we can actually operate on code, and we have been doing a bunch of stuff on things like program simplification, program transformation, the possibility of essentially a grammar checker for code, so that as you type it in, it can tell you that's a really lousy way to write that. Here's a better thing to do, to make the auto-suggest mechanism not just suggest, individual function names, but suggest whole blocks of code to put in. Those are the types of things that we're trying to do. Now, I should say that in terms of natural language, one of the things we're doing is we have a mechanism for adding new natural language grammars to our main grammar, and that's something that sort of the idea is that you make use of all the existing natural language understanding system, then you add your own little pieces. So, for example, typical case is set the alarm for 5 minutes before sunset. Okay, so 5 minutes before sunset is a time construct that we understand, our natural language understanding system can deal with. You can add the little piece of grammar about alarm clocks, and we have a whole algorithmic language for representing, natural language to add things like that. We're gradually, unrolling sort of the richness of the stuff that we built for Wolfram Alpha and putting it in a form where people can add little fragments of language, and then, the piece that says there's this sort of token thing that represents, time, and then you can take that and you can say, do this action based on that time. So people will be able to do pretty good experiments, I think, with natural language programming, and it's a pretty interesting area. I don't know how far it will go. My guess is that there are sort of three paradigms for programming. There's natural language, there's structured language, and there's visual programming, and all three of those have their place. And the real trick is to be able to integrate all of those together to get the best of all of them. Yes, please.
Extend and encapsulate some knowledge about some area which is not in the core Wolfram Alpha system.
Right, so, obviously that's why this is called a language, because you can write things in it. That's exactly, any of the things. So depends what kind of knowledge you're trying to represent. If you're trying to represent algorithmic knowledge, that's something that we're rather good at that. If you're trying to represent sort of factual entity property value type stuff, that's very easy to do as well. Anything, since most of those, most of the system is written in the language itself, it's kind of proof that you can extend it using the language. Now, the typical use of this will be people have, they're exposing some API for something. That API will be resting on top of a bunch of code that they've written in the language that specializes it for the particular thing they want. I mean, some fraction of the time, if we've designed our language well and we put in the knowledge that people find useful, then there will be a lot of 2 or 3 line pieces of code that will be very useful APIs, but also there'll be plenty of things that involve 100,000 lines of code that define an API that's based on some very sophisticated thing that was nothing that we imagined being able to deal with. Yes?
I have to say I'm really impressed with the level of integration you guys have achieved with the language. Along those lines, I have a question just about how you guys went about developing this. How did you handle this level of interoperability? How much code did you write in-house, and what kind of principles did you guys go about deciding what to leave in and what to keep out?
Okay, so I've been at this for something a bit more than 30 years. So the first language that I developed was called SMP, and it was a symbolic language. And I made many language design mistakes in that language. So that was very useful to have one language where I could try things out. And then when I started designing Mathematica, on which the Wolfram language is based, I at least had one set of mistakes that I didn't make. Now, in terms of how one achieves the integration, unification, and so on, that's been the story of my life for a large number of years. I've been the one ultimately responsible for making sure that all the pieces fit together. And that's, there's a process, I've tried to develop sort of a way of thinking about things and kind of a company culture and so on, where we know how to do the kind of design that makes things fit together. The basic thing that happens is, when you look at an area, at first, people say, well, we need this feature and that feature and the other feature, and it's all a big mess, and they're all little features being added all over the place. In the end, what I found is you have to kind of grind down and try and understand what are the fundamental primitives that are actually going on. What is the true understanding of this area? For me, I've got across a vast number of areas. I finally understood these areas after we've kind of ground it down to understand what the primitives are. Sometimes it's taken me more than a decade to understand different areas. Like there's one area which is, this is a painful one, but if you do multivariate calculus and you're doing vector analysis and you have these different coordinate systems and so on, you're working in spherical coordinates and you're doing this, that, and the other. It's taken me basically 25 years to understand the math clearly enough to be able to actually, and in the end, I didn't figure this out. In the end, some people at our company figured this out, and then they taught it to me, and now I think I understand how to think about this in a way that's actually clean and it actually all makes sense and fits together. But that's the pushing to sort of grind it down so that you really understand how it works and you have the right primitives. The amazing thing is that when that happens, things do tend to fit together. If we have a definite paradigm for working, and once we've got these primitives into that paradigm, it fits together. Now, when you build a system like this, there's this notion of sort of precedence. Like, have we ever done something like that before? And you have to kind of there's a trade-off between everything is based on precedent, and if you do that, nothing new ever happens. And so you have to, it's a tricky judgment call. When do you add something that is fundamentally different? And when is the thing that you're adding something that is important enough that it should have something different be done? Another thing that happens is, what happens if you made a mistake? What happens if you realize that you built something in the system that wasn't quite right? Then, one of the things that I've noticed is that my principle is we just figure out what is right, and then you might think, oh my God, we'll never be able to get compatibility with what we had before. That's almost never the case. Almost always you can make a bridge. Once you know what's right, you can make a bridge from the thing that wasn't quite right to the thing that is right and still maintain compatibility, and that's been one of the sort of things. Another thing that's happened in the design of the system is, when I first worked on Mathematica and so on, I thought heuristics were just horrifying things, that one could never know heuristics, because anytime there was a heuristic, people would get confused, you wouldn't know what the system was going to do, it would all be disaster. Okay? And then we started working on Wolfram Alpha, and what's interesting about that is that the design of Mathematica and sort of the core of the Wolfram language is very precise and structured and elegant and all that kind of thing. In Wolfram Alpha, the goal was just have people type in natural language and do what I mean, so to speak. And just anything goes, and just do the thing as heuristically as possible. And what I learned, to my surprise, is that when you have enough heuristics, there's a logic to heuristics that's sort of all its own. That you eventually get used to building things with large numbers of heuristics. And it, in fact, all still fits together. It's in a different way. It fits together differently from the way that a precise language fits together, but it still fits together. And what I wasn't sure about, and what's been pretty interesting recently as we built out the Wolfram language, is how you merge this kind of heuristic mess over here that has to be a heuristic mess because it's dealing with the real world, and the real world is kind of messy, and with the sort of precise language over here. And I think these things like, being able to have these fragments of natural language that define entities and things like that, that's an important way in which you sort of bring those two methodologies together. But this question about what's a primitive, what do you put in, the main thing is just you have to drill down and understand the things as well as possible. Another thing, so I'll give you an example of something, my ideas about language design have evolved a bit over the years. So I'll give you an example of something that's evolved in the last decade or so. So I used to believe that you should keep the language, if there were things that could be done with a trivial idiom, then just let them be done with a trivial idiom. What I realized more recently is if everybody's using that idiom, you might as well give it a name. Because if you give it a name, then the code becomes more readable and you're more able to reason about that code. Sort of a simple point, but you might have thought, why bother to do this? It's just, two little functions stuck together. Why call that, why give that a different name? Well, if there's a way in which you can have a concept in which that helps people conceptually to see that those things are some different name, that's worth doing. The other thing to say about design of language, the naming of things is one of the most horrifying processes. I mean, it's taken, the amount of time it takes to come up. Sometimes I'm lucky, and some function, I'll understand what it does, and immediately I'll know what it should be called, and it's all done. Other times it can take days of grinding through with, trying to figure out what a function should be called. Why does it matter? It matters because that's the cognitive hook that people have for this thing, and if you've got the wrong name, it's lost. And the typical mistake is that you have a particular use case in mind for this function, and you end up giving it a name that is based just on that use case. And then forget it, nobody will ever use it for anything else. On the other hand, if you give it a name that is too abstract and weird, people will have no idea what to do with this function. So it's a complicated trade-off. And there are a few cases where I regret some functions with the names that they have, but it's fortunately not too many regrets. And you can usually tell, I've become fairly good at telling whether the name is right. Sometimes very frustrating because I know it isn't right, and we have to keep on iterating to get it right. But that's one of the things. Yes.
Suppose you're looking for a function like the one that diagonalizes the wiggle a jig. How do you find the name of the function?
Type it into the help system. I mean, that's the it's just that's the best thing one could do. Now I think the other thing we've done, if you look in some of these places, if this is even working, why is this? This is misbehaving in the most bizarre ways. Okay, if I type something like this, what is going on? I'm just completely mystified. Usually, there's a little set of predictions that come up underneath that. I'm really confused. This is a sick creature. What's it doing? No, but I've done demos for years. They don't usually. Yeah, it was coming up earlier, right? I mean, that's just weird. Oh, who knows? I'm gonna restart it again just because I want. Did I press the wrong thing somewhere? Maybe I told it to not to disappear forever. I don't usually do that, so I don't even know how to get it back. Okay, I'm going to try. I'll tell you what. I'm going to launch. All right, let's kill this again. Let me launch this again. One more time. See whether this will work. I'm going to show you something which is sort of an interesting thing because it's what we call our predictive interface, and sort of the idea there is, let's see if anything works here. Oh, that's just bizarre. I'll tell you what. Let me just see one last thing to try. Let's try. That's an old version of Mathematica. I don't. Let's try. I run a software company, so I have to show you the absolutely latest. Okay, 328. That's fairly recent. I think this feature should be visible there. If it isn't, then I'll be. Oh, there we go. Okay. So this is so what we're seeing there is, in this case, x squared minus 1. Okay, it says, do you want to plot that? Okay, I'll plot that. do you want to change, add a gray frame to that? Okay, I'll add a gray frame to that, and so on. So that's an important kind of idea for leading people through, operations that they might want to do. It's sort of funny because what ends up happening is, how do you figure out what to put in that suggestions bar? Well, you end up having to do a lot of computation to figure it out, because every one of the things that it's suggesting there, it already figured out what's going to happen if you do that. So, given the result of a computation, you're then branching off lots of different computations, figuring out which one is going to heuristically produce something that's interesting, and then showing you that as a suggestion for what you might want to do next. So that's one way in which we try to help people find the whatchamajig function or whatever. Yes.
So one thing that's not clear is, since you're putting this or deploying it in the devices, who draws the boundary, what goes in the device and what goes in the cloud, etc.
Well, so the idea is that the whole engine is in the device, and the whole engine is in the cloud. And if you have a device which is taking data locally, and it is often useful to grind down that data locally before you use the communications bandwidth to send it up to the cloud. So it's really the vision is, it's the same piece of code. You could run that piece of code in the cloud. If you have a fast enough communication from the device to the cloud, you can run that computation in the cloud, or you can run it locally in the device. It'll probably be slower in the device than it would be in the cloud, but you won't have to spend communications effort.
Right, but I presume that the entire, humongous system that you were talking about that's back in the cloud can do a lot more sort of intelligent computation than the
only thing that's missing in the device is sort of data about the world.
Right.
The real-time data feeds, what earthquakes have just happened, it's got to go to the cloud to get that. But all of the algorithmic computational stuff, that fits inside the device. I mean, that's the sort of interesting thing that's happening now, is that, I've waited for this for a long time, being able to have a little tiny machine, even a Raspberry Pi is pretty small, but it's about to get even much smaller than that. We talked about at CES, we talked about getting this working on the Intel Edison SD card-sized computer, and that's a really small thing. The thing that it's been a long time coming. Being able to get our whole engine to run on something that small, but I think it will be the case. That sort of the generic object, however small, can run the engine. Then the choice of what computation you do locally versus in the cloud, that's a detail of particular application areas.
So
Yes.
does that say something fundamental, that this much stuff that's in roughly a gig and a half?
Yeah, I mean, it's actually
That's what it's more.
It's
all that fits in.
Yeah, I mean, the algorithmic, the minimum footprint is around a few hundred megabytes. And you can start doing stuff at that size. When you start having lots of data coming in and so on, it gets a lot bigger. But yes, the sum total of human algorithmic knowledge is not as large in megabytes and gigabytes as you might think. And we've been kind of one of the things that's happened is, because of sort of our long-time software engineering lineage, we've been pretty miserly with memory usage and things like this, and so the system is really quite efficient, which is something which when people have built software more recently, sometimes they just don't worry about that. But because we started building this a long time ago, we sort of developed a culture of worrying about that from a software engineering point of view, and it seemed like, who cares, for a long time. But now when you want to get it on a device, a really, really tiny device, you care again. Yes?
You mentioned the system has knowledge about the world, and everything in your system is a symbolic expression. How is this, the stuff generated? Does it follow the web? Does it automatically, is there algorithm that automatically go out and generate this information as symbolic?
No. So we've been, for the last probably 10 years or so, we've been kind of accumulating computable knowledge about the world. And so the biggest place we've used that is in Wolfram Alpha, which shows up in lots of places like Siri and things like that. And that knowledge is based on us going to primary data sources and and sort of making that data computable. And this has been a huge effort, going across thousands of different domains and working with God knows how many different providers of data and so on. And we've been the organization that's probably been doing the most in sort of integrating different kinds of data together. It gets, it sort of gets easier after you've done 1,000 domains. It gets easier to do the 1,001st domain in some respects, because we have very streamlined techniques for representing the knowledge and so on. In some respects, it's amazing because the 1,001st domain will always have something bizarre about it that's never been seen before. But it also helps that you can cross-check a lot of the data. When you get data about a new domain, our ability to validate that data is vastly higher from having all the other domains be computable. I mean, what's the thing that's notable is you think, well, you can get data from all kinds of places. Well, maybe that's true, but you can't get computable data. You can't get data that's clean enough, understood enough to actually be able to use as part of a computation. And that's been the thing that we've been sort of working towards with Wolfram Alpha, and which we've now we really have to have that to incorporate the data in the Wolfram language. And so we've got, I don't know how many terabytes of data we have now as sort of raw numerical, string-like data and so on. It's somewhat bigger, I think, than the text content of the interesting web, so to speak. So it's not something that will be forageable. Even if we wanted to, there isn't enough of it out there on the obvious, textual web. I think it's interesting to see how we make use of stuff on the web. We make use of things, things like Wikipedia. The main way we end up making use of it is for the folk information that it contains. Like, you may have a systematic data source that gives you the official names of every city in California, for example, but you don't know that, San Fran is not something which is in the official database of names of cities. And that's something that's easy to derive from something like Wikipedia. So that's a place we use it. Another place we use it is in things like the relative popularities of things. That's important for disambiguation and so on. And for lots of other purposes, but that type of thing. Yes, please.
Could you bring up the grid that represents Wolfram language? Yeah. So when you look at those boxes, there's the possibility going forward for the language of enhancing individual boxes or adding new boxes. So my question is about whether this is intended in the long term to be an open or closed system. Closed in the sense that you get to arbitrate language, source of data, algorithms that are added. And open in the sense that you absolve yourself from being the bottleneck, that everything has to go through you. Which do you intend the system to be in the long term?
It's been pretty closed for the last 30 years. I mean,
Is actually one.
If people could come to us and say, here's this great thing, and let's add it on, and it looks perfect, I'd be thrilled. Okay, I don't think that's going to happen, because what's ended up happening now. Having said that, this issue of how do you make everything really unified and so on, this is hard work, and people, increasingly. I guess, if the language becomes sufficiently popular and sufficiently many people really understand the paradigm, then I think it is more conceivable that there will be pieces that people can contribute that can actually just be slotted in. But if you look at, with Mathematica, for example, there are plenty of people who've created third-party packages and so on with it, and they're perfectly good. They're nice things. They're very useful in some particular vertical area. But if we really look at them and say, should this be part of the language? The answer is no. The answer is this is a great prototype. It's a great thing that that can serve people who are prepared to dive into that particular world and understand this stuff. But is it something we can incorporate? No, we'd have to do a lot of work to incorporate it, because in a sense our standards are much higher than the typical standards of sort of the library edition type thing. So I suppose my main statement would be, I'll be really thrilled if it gets to the point, and I don't think it's impossible, I don't think it's super likely, but I don't think it's impossible that it will get to the point that there's enough kind of cultural understanding of how to create things. I mean, I suppose an interesting question would be, if you look at other large systems, when has been the case that people can actually add pieces to them and sort of match the culture of what's already there? And I'm not sure I have a good answer to that. There are things like adding to OpenStreetMap is a hell of a lot easier than adding to a language that's been built in a very integrated way for 30 years. Yes.
Another answer to that question is that every single one of those has deep connections to at least 90% of the rest of them, if not all of them. And there are a lot of gaps where somebody could come in and put something. And I can imagine there's 3, but I don't know what they are.
Yeah.
So
we have a big
that's
map
sort of the
of
problem.
things that we
When
want.
somebody comes up with, they've got their problem, they don't care about either of those. They've got their problem.
Yeah, right. So that's what typically happens. Is that there will be, I hope, tons and tons of stuff built that is sort of vertical pieces on top of what we already have. But you're right in terms of we've tried to cover the kind of the broad horizontal set of things that are needed. There are others. We hope our work is not finished. This is a long-term project.
A different reformulation would have different categories, but they all have this connectivity that is supposed, not the classification.
Yeah. Please. Yes.
I suppose this is a question more about Wolfram Alpha, but how do you purge the system from old information that's no longer considered to be the best knowledge today? Like if you ask the system, list the planets.
Yeah.
Well, that's the answer.
Yeah, right. Doesn't say the range of them. But yeah, I mean, that comes up at all levels, whether it's restated financial data, whether it's other kinds of things. I mean, how does it work internally? We have a curation schedule, and things we know. This thing. Sometimes the things that come in as feeds, where it's updated every, the flight tracking data from the FAA. That comes in as a feed, and we keep it working. It's if it fails, we know immediately that it's failed. It's more difficult when it's something where there's a report that comes out every quarter or something, and you have to make sure you get it every quarter, and that the thing didn't change its format and so on. And then there are really one of the more macabre pieces of the curation process is the obituary feed, and so that ends up being we have it goes to our we obviously have site monitoring, and it goes one of the many functions of our site monitors is they get these obituary notifications that come from news sources and so on, and then they have to click on something to decide is this a plausible one, and or is it some report of something that's just complete nonsense, whatever. But so that's an example of something where it's not on a schedule obviously, and it's something where you have to have a process for doing it. So what we've tried to do is develop all these processes for being able to keep information up to date. I mean, there are also other complicated things where there are disputed kinds of information, and information which in one part of the world people think this, in another part of the world people think that. I mean, one of the ones that we had was is a rabbit a pet or a food? That was one of the things that was that went wrong at one point. Yes.
So I think this is a fabulous system for exploring the world and data sets and things like that. And I'm just wondering though, are people going to hit a wall? Because you've got the principle of automating as much as you can. So someone can come in and say, show me a picture of an owl, or tell me about this cat breed. And they can get a picture. Can they get, if they say, okay, show me another one. Is that there? How much do they have to dig in? If they've got something, I know you had a principle on one of your pages about having knobs and being able to get down deeper into it. So you do the detecting edges. Can I get into the edge detector and change a parameter there to make it more sensitive or
Sure, I would think so. Let's find out. Let's take that as an example, okay? So let's look at edge detection. Okay, so this is the simple version of edge detection is you say edge detect on a picture and it does something. Okay, so let's look at details and options. Okay, so here, in 2D, okay, this is 3D edge detection for 3D images. So here it's telling you there are 3 different specific edge detection algorithms, Canny, Shen, Kasten, Sobel, which you can use. There are various options here. There's a couple of parameters in the edge detection for the threshold and things like that. So the answer is you can, there are knobs. I mean, I would say that one of the bizarre things that I've noticed over the years is, in Mathematica, we had a default 3D viewpoint. We have a default 3D viewpoint. Okay, so I've looked every so often at, science journals and things like that. And the question is, what fraction of all 3D plots that were obviously made with Mathematica have the default viewpoint? And the answer is, 99-point-something% of the plots have the default viewpoint. Now, we chose it reasonably carefully. I don't think it's, optimal for everything, but, the defaults are important, but, we want to provide the knobs and so on for people to change them if they want to. Now, an interesting question is, to what extent are those knobs, when we have a meta algorithm, Are we better than the humans? Is the autopilot better than the humans, so to speak, at actually figuring out what to do? And some of the places where people get go very wrong is where they say, oh no, I can figure this out much better than the system can figure it out. And they can't. And they simply get it wrong. And then they say, oh, the system's broken. Well, if they just set it on automatic, it would have been just fine.
Well, that brings up another question about when people talk about language, the almost natural thing to talk about is a conversation. And most of what you've been showing has been imperatives. Do this, do that.
Yes.
Maybe there's the ... for disambiguation if it's in there. So the system says, I've got something to say if you want to hear it. But if you do something, let's say you do the classify, and you say, oh, that doesn't seem to work. I'd like it to be, and you want to say something about that, a conversation back and forth. I don't know how possible that is right now.
Well, that's an interesting question. I mean, I think this predictive interface and suggestions bar is the beginning of that type of thing. I mean, I sort of, one of the most horrifying things, you've got a big piece of code and somebody gives you a big piece of code, and somewhere inside that code, the code asks a question. And so you're running somebody else's code, and somewhere it says, should A be assumed to be greater than 0? Say, I don't have the slightest idea. That has to be avoided. But I think, this question of being able to, how you iteratively get the right result, I think our suggestions bar thing and the things we're trying to do with code transformation and so on, that's where how we're trying to get to that. Yes?
What do you think are the advantages of treating everything as a symbolic expression rather than an object or a list or something?
Well, because we get to see any one of these things can be sort of thought of as equivalent to any other. But when I say the point about symbolic expressions is they can have kind of they're just trees. They can have arbitrary stuff in those trees. They don't have to have any particular form. They're not they don't have to be arrays. They don't have to be this. They're just an arbitrary. It can represent. It's hard to imagine something you can't represent as a symbolic expression. And that's really the point. And also the very expectation that you can just plop the symbolic expression somewhere and it will just be happy on its own. If it isn't symbolic, then if you type X, then if X hasn't been given a value, you get an error. And the important thing is that you can just have X without insisting that it has a value. Yes?
There seem to be pretty large-scale company-backed efforts to structure all this data. Yours, Google Knowledge Graph, Facebook Open Graph. These are all sort of, way kind of semantic web-ish, but done internally in-house, get it to actually work. Do you see any kind of integration happening in the future, any kind of convergence? Do you see the systems remaining separate? Is there already integration? Like, where do you see this world continuing to be separated from the Tim Berners-Lee semantic web model, or?
Right. So I mean, in terms of what we're trying to do, so the thing that we have is a weird sort of algorithmic ontology. So a lot of what's been done previously in sort of ontologies is very static. It's like, is this a member of that? Is this whatever? We have something where we have a way of representing, planets which are moving and, have different, have positions in space and they're changing and so on. And it's a sort of more algorithmic kind of thing. Now, in terms of, actual, entity identifiers and things like that, it's pretty easy, and we actually have the, mappings between entity identifiers of different, different kinds of bases, and we'll actually be exposing that kind of thing. In terms of what does this mean for the promise of the, the semantic web or whatever, I think that, I think with WDF, for example, we actually have a practical version of some of the goals that Tim Berners-Lee and so on had with the semantic web, in the sense that, and I think that will be visible in things like this device, data from devices and so on. It actually matters that this device can report its, temperatures in centigrade, and we know it's in centigrade, and so on and so on and so on. I think that's the kind of direction in terms of, what we've been trying to do is, one thing is, the entities, their relationships. Another thing is kind of the algorithms and models that determine how those entities behave. Another thing is the way to refer to those things with natural language. These are, we've been trying to do all of those pieces, little different from those other folk. We're a smaller company. We're only 700 people, so it's, there are different constraints, but we've been we've been doing what we can, so to speak. Yes, please.
Another question regarding your backend, like the computing system where everything runs. So how is parallelism managed there? So say, for example, I launch some sort of a very big number crunching job using the English language. Do you automatically parallelize it, or is it broken down into chunks which...
Right, so the parallelization right now...
I mean, if I just say, let me just run this in some place. Let me go here, and let's say parallel table, and you have to watch fairly quickly when I do this because it won't take long to happen, I think. Let's say I do something like this. What will happen is you'll see it launching a bunch, I don't know how many processors this particular computer has. Let's watch. Okay, it launched 4 kernels there. So, and then what it did was it took those pieces and it distributed them across. Actually, I'll tell you what. The way to really see this is the following. Let's just say parallel table of $process ID. Okay, so then what you'll see is that there are. Well, let's just use the language. Okay, there we go. So it allocated, 25 copies of each process ID showed up in that list. So it distributed that across those 4 things. We have decently good load balancing mechanisms and so on. This is pretty coarse-grained parallelism. It's really the whole engine is being done. We have actually a thing. We have a thing, the Wolfram Launch Manager, which is a thing that uses multicast DNS to try and say, I'm a service here. You can call me. The idea, for example, on Raspberry Pis, that will be launched by default in the OS. And so if you have a big network of Raspberry Pis, you'll be able to discover all the Wolfram engines living on those Raspberry Pis, and it will be possible to just run parallel table or something, and it will just immediately run across your whole. Once you've set up those Raspberry Pis and said you're going to use all of those, it will just work automatically. I mean, we're within the system. There's a bunch of multi-threading stuff that goes on deep inside the actual engine, but that's a low level. Then there's a much higher level of parallelizing across engines.